All right, welcome everybody, and thank you for coming to my presentation today. I'm going to be discussing all-atom modeling of cellulose microfibril assembly, which is a particularly interesting topic in the field of biofuels. And before I begin, I'd like to give special thanks to Dr. Kwanzaa and Dr. Yingling for their continued support on this project. So just to briefly discuss cellulose and its importance in biofuels, biofuels in general have gained traction in recent years due to the fact that they're renewable, so you can essentially continually farm a source of energy, and then also because they're natural carbon sinks, so you combat this sustainability issue at the same time. However, traditionally, biofuels kind of run into an issue with food security. There's an ethical dilemma. Can we take crops that should be solving world hunger and use them to make fuel? And then also an efficiency issue. Interestingly enough, with cellulosic biofuels, you combat this food security problem, so you can use parts of the plant that aren't used for food to manufacture these fuels, such as the roots and stems, but you don't escape this efficiency problem. There's very few enzymes that can efficiently degrade cellulose, and then we also know very little about the process to enhance it. So we don't know how these fibrils form and how to manipulate it for faster degradation. So essentially that's where our research comes into play. We're modeling these fibrils, seeing how they behave, seeing how they form, and seeing if we can lay the foundation for manipulation. So before I get into the in-depth part of my presentation, I wanted to introduce two general topics. So the first one being, what is cellulose? And essentially cellulose is a complex carbohydrate, which is a long chain of units. Each unit is a repeat unit and it's identical, and it consists of carbon, oxygen, and hydrogen. In the case of cellulose, each unit is glucose. So you've got this long string of repeating glucose units. And although it's not important to know the exact conformation or the chemistry behind this, it's good to become familiar with the overall structure. So it's essentially, you can think of it as a chain, whereas a physical chain made out of metal has these continually repeating units. Each unit's exactly the same. So then one other topic I wanted to introduce are what are molecular dynamics simulations, because that's going to play a large role in our research. And essentially what they are, they're computer simulations that employ fundamental physical principles to predict atomistic behavior. So you take each atom, define it as a hard sphere, and then give it parameters from experiments. So the parameters are actually based on experimental findings. And then you develop these energy terms for different parts of the system. So you've got non-bonded energy, the energy between atoms, for example, bonded energy, as well as energy to describe different angles. And essentially what molecular dynamics seeks to do is minimize the total potential energy. And while it does this, it's particularly neat because you get atomistic resolution, so you can see how the atoms behave, and then also temporal resolution, very high temporal resolution. So you can watch how they behave on a femtosecond level. So just to go into the overview of my research specifically, we essentially narrowed in from these biofuels to electron microscopy images that show these circular-like objects on the left side of the page with fibrils extruding. The circle is a cellulose synthesis complex, which consists of enzymes that synthesize individual cellulose chains, and then the fibril extruding. So although we know there is this complex and a fibril that comes out of it, little is known into the dynamics in between, so how these individual cellulose chains interact to form the fibrils, and then also the interactions that hold the fibril together. So transitioning to the artistic representation, you can see the cellulose synthesis complex in gray, which is a set of these 18 proteins, which are grouped into 6 groups of 3. So each group of 3 is a trimer and is colored differently in our system. And then they group into an overall hexagon. From there, we developed a computational representation with the all-atom cellulose synthesis complex and all the chains. Then we remove the protein due to computational feasibility. We can only handle a certain amount of atoms when we're running these simulations, and then ran molecular dynamics. Again, molecular dynamics are special because they allow for spatial and temporal resolution that experiments don't. So to go a little bit more in depth on the computational methods, we essentially took an experimental structure, 6WLB, which is a protein or a trimer. So it consists of 3 of these proteins, and then arranged it into a cellulose synthesis complex based on C6 symmetry. So again, this complex is you can treat it as a hexagon with 6 of these 6WLBs, which consist of 3 proteins. From there, we added successively longer increments of chains to model different degrees of polymerization, remove the cellulose synthesis complex due to computational feasibility. It put us over 3 million atoms, and the top we can handle with a reasonable performance is 3 million atoms. And then once we remove these proteins, we replaced it with restraints. So the effect of the proteins is still there, it's just artificial, and then perform molecular dynamic simulations. So just to show a current status of the system, from left to right, we have 20-mer, 30-mer, and 40-mer. You can see that they progress in size, so the 20-mer being around 800,000 atoms, with the 40-mer being around 1.7 million atoms. But they decrease in the time step they're at. So it takes the larger system you have, the longer it takes to run. So the 40-mer system is only at 470 nanoseconds, while the 20-mer system is almost at a microsecond. You can also notice a few distinct visual trends moving from left to right. So in the 20-mer system, you see very little aggregation within a trimer, and then also you don't see bundles forming between different trimers. It seems somewhat random. Transitioning to 30-mer, you get a lot more aggregation within one trimer, so you can see a lot of the chains that are colored the same are aggregated together, and then they start to come together between chains. And then in the 40-mer system, you can see you get a lot more bundling within a trimer, and these chains interact between trimers. This is consistent with the 50-mer and 60-mer simulations. These are at a lot lower time steps because they're a lot larger system size and they were started later. So the 50-mer system has about 2.1 million atoms, and the 60-mer system has about 2.7 million atoms. And you can see these are forming large bundles within a trimer, so the same colored chains aggregate pretty well, and then they're also starting to come into contact with other chains early on in large proportions. In order to quantify this, we ran analysis on energy. So we've got on the left side energy within a trimer, intra-trimer energy, and then on the right side energy between different trimers. The blue represents the 20-mer, green 30, red 40, cyan 50, and the purple 60-mer systems. And you can see that interactions within a trimer are a lot more influential at earlier lengths, whereas interactions between trimers are a lot more favorable or influential at longer lengths. So on the left side, you can see it trends up from 20 to 30 to 40 and then remains constant, whereas on the right side, the interactions between a trimer remains relatively constant and then trends up for 50 and 60. And essentially what this is telling us is that these chains, as they're coming out of the sese, you would take a length of 10 first. It's a lot more influential that this, as it grows, forms interactions between a trimer, and then once it gets long enough, it starts to interact between different trimers. I also presented the number of clusters, and so the important takeaway here is that as you increase the degree of polymerization, the length of the chain, you can see that larger clusters, so a fewer number of clusters, but they have a larger number of chains, form at faster rates at higher degree of polymerizations. So just a summary on the presentation today. Intra-trimer interactions are sensitive to chain length at the lower end of the studied degree of polymerization. From 20 to 40, interactions between trimers become more influential from 40 to 60, which kind of illustrates the process of how these fibrils form. And then also kinetics suggests that as the degree of polymerization increases, the cellulose chains form more complete aggregates at a faster rate, as we talked about on the last slide. And essentially, the takeaway from these results is that they provide the foundation for biochemical engineering of more efficient cellulosic biofuels in the future, which is going to combat our current issue with biofuels and possibly bring them back to the forefront of the fuel industry. That's all I have for today. Thanks.